is the same thing. This, this, this. Now, slightly not the same thing because this is a set, this is a logic statement, but they represent the same thing. Okay? So now, how about less than a? Absolute value of x less than a. Now that is just mimicking the same thing, minus a less than x less than a. The graphical representation will be this one, minus a and a, but now with open circles on both a's. If I want to represent this as an interval, it'll be minus a, comma a. Okay? That's what it represents. Now, if I flip my inequalities, right? Absolute value of x greater or equal than a. What would that be? Well, it's the negation of the second one, right? If I apply the negation of being less than a, it's just saying greater or equal than a. So it's the negation of this. So what's the negation? And you see why I'm doing it backwards. It's easier. Of this representation. Well, we still are in minus a and a, but now I'm going opposite sides, and I'm bolding a. Right? Because it's the negation of this one. Now, how do you write this in terms of something related to inequalities? Well, it's x greater than a, greater or equal than a, or x being less or equal, greater or equal, x being less or equal negative a. Okay? That's what it means for absolute value of x being greater or equal than a. Okay? What will be the interval notation for this? It will be from minus infinity to a included, union a to infinity. Okay? Minus a. Now, I know this video is going to be long and tedious because I have to explain all of this to really grasp the idea of the definition of limits. So bear with me, okay? And then absolute value of x being greater than a, very similar to this one, is x less than minus a, or x greater than a. Graphical representation is basically the same without including the a's. So I'm going to write it as fast as possible. I said without including the a's, and I include them. And then here is the same thing with the union sign. That's union, by the way, it's not u. Okay? So that's all those four properties are very important for the definition of limits. Okay? So let's go back to the definition. We are here. So let's talk about the part from the right of the first part. X minus c less than delta. Which of the four properties that we define are we going to choose? The second one, right? Because it's the one that has less than to the right of the absolute value. So look at this definition. That's exactly the one we're going to use. So let's go up. Let's turn a little bit to the right. Well, more. There you go. So absolute value of x minus c less than delta. By definition, by the same property that we defined earlier, this is if and only if what? Minus delta less than x minus c less than delta. Okay? Delta is a real number greater than 0, so we can apply this definition exactly the same way. Now, what will be what can I do now? Well, notice that I can isolate for x. Because in the property below or next to it, there was just x. I can isolate x by adding c in both sides. So if I have minus delta plus c less than x minus c plus c, which is just x, less than delta plus c. Okay? Now, how would that look like in terms of my inequality or my representation, my graphical representation? Well, I have a c plus delta or delta plus c, and I have a c minus delta, right? I don't include them because there's no equality, so it's open. And x is between those two, so x is everything between this. Okay? Now, how would you write that in terms of intervals? So it will be c minus delta, comma, c plus delta. And that will be your interval, right? I don't include the endpoints because there's no equality here. So now that we understand the definition of absolute values, it makes more sense. What does absolute value of x minus c less than delta mean? It's just saying that all the values of x that are between c minus delta to the left and c plus delta to the right. Okay? And c, remember, is a real number. It's a constant. It's a fixed real number. It's not a variable. Not a x. Not like x. X can be anything between them, but c is fixed. C is just one number. Okay? So this delta gives me a range or a distance between c and to the right of c and to the left of c. Right? Because c hits in the middle. C is right here. Okay? So delta, it's a positive number. So if I'm adding if I'm adding delta to c, I'm moving to the right of c. If I'm subtracting delta to c, I'm moving to the left of c. That's why we use delta greater than 0. Okay? So if delta is 10, then whatever c is, c could be 1. Then to the right of 1 is 10. To the left of 1 is negative 10. But c could be 10. So to the right of 10 will be 20. And to the left of 10 will be 0. So notice that the placement of c is important. And the distance or the delta is also important because it's going to give you that distance between c to the right and c to the left. Okay? That's basically what this craziness means. Okay? So now let's go to once more detail about the inequality. Notice that it says that x minus c is greater than 0. So greater than 0. What does that mean? Well, by properties, absolute value of x is already greater or equal to 0. But if we're restricting ourselves that x minus c is greater than 0, that means that x minus c cannot be equal to 0. Okay, that's very important. So x minus c is not equal to 0. Therefore, x minus c is not equal to 0. I mean, the absolute value is not equal to 0, so x minus c is not equal to 0. Therefore, x minus c is not equal to c. Boom. What does that mean? That in my representation, if I were to mix those two together, so 0 less than absolute value of x minus c less than delta, if I were to combine those three things together, my geometric representation or my real line of this will still be c minus delta to the left without including, c plus delta to the right without including, but a new difference comes into play. C is open. Okay? Because x cannot be c. So x can be anything between this but not necessarily C. Now I'm going to throw that word necessarily. It could be C, but not necessarily. So that's the power of limits. That you can find a limit, but it doesn't have to be defined at the point. So at that point, you can have a vertical asymptote. You can have a different value. You can have nothing, not be defined there. And there could be a limit. Okay? That's very important. So how would I write this in interval notation? Again, it will be open C minus delta, comma C, open union, comma, parentheses C, comma, C plus delta. Okay? And boom, we've connected what it means with the graphical representation with the interval notation. Okay? Now let's go back to the definition. So, if that condition applies, then the absolute value of f of x minus L is less than epsilon. Just like we did before, we're going to do the same thing for this one. So let's try to define what absolute value of f of x minus L means. So absolute value of f of x minus L less than epsilon. Again, we use the property of absolute value. If and only if. Minus epsilon less than f of x minus L less than epsilon. Okay? We're going to do very similar to the one before. We're going to isolate for f of x. So minus epsilon plus L less than f of x less than epsilon plus L. Okay? Now, my geographical representation of this is still going to be a line, but because this is, L is in what? Range, right? We said that earlier. So I'm going to use a vertical line instead of a horizontal line. And then I'm going to connect the two. So for the graphical representation, I'm going to use a vertical line. So again, L is in the middle, just like before. So L is playing the role of C for the domain. Okay? But here is the range. And then over here, we have an open circle for L plus epsilon, and then an open circle for L minus epsilon, and then notice that there's no zero greater than. So f of x is equal, could be equal to C, to L, my bad. Okay, so f of x could be any number between that. Okay? And there you have it. Left. So this is the visual representation. This is the inequality. Now, how would I write that in interval notation? Well, it would be the same thing. So minus epsilon plus L, comma, epsilon plus L. Some books have them as L minus epsilon. It's the same thing. L plus epsilon. Okay? And there you have it. I've broken apart all of the inequalities, and now we're going to put them together. Okay? So together will be a two-dimensional space, right? So let me see if I'll try my best to avoid using my pen, because oops, I think I have to give it color, right? Yes. So let me give this, just give me 1 second. There you go. Sorry. Okay. Wait, I filled it with colors. There you go. Bam. Okay. Then, okay. Then, yes, again. I'm going to use a different color this time. Okay. So, how would that look like visually or geometrically? You have a function. That's my function. I drew it continuous because it's nice, but it doesn't have to be continuous, remember. Now, this is f of x. right? It's my function. This is x. This is y. I'm going to change the color. I don't like that color. Now, imagine that I want to find the limit when x approaches c, and c is the number here. That's c. Okay? So, c, remember, it doesn't have to be defined as c. So I can erase that bubble there. Oops. Okay? So that means c, f of c may not be defined. Okay, that's very important. Now let's look at c plus delta. Where is c plus delta? Well, it's delta units to the right of c. So c. This is c plus delta. Where is c minus delta? Well, it's delta units to the left of c. C minus delta. Okay? And now, how would that look like in terms of f of x? Well, this value, it's called L, right? Then what's L plus epsilon? Well, it's epsilon units to the top of L, right? And what's L minus epsilon? It's epsilon units to the bottom of L. Okay. So, what's the mechanics of the limit? Remember that I said that for every epsilon, there's a delta? Okay. Imagine that I take epsilon being 1. And I have a fixed L and a fixed C. If I choose 1, then there's a delta in the bottom next to C that exists for that epsilon equal to 1. Now, shrink epsilon. Shrink it, shrink it, shrink it, closer and closer to L. Then what's going to happen with delta, or what you want to happen with delta, is that it also shrinks and shrinks closer to C, right? To the point that they're so close that they're almost touching. But because x cannot be C, or it doesn't have to be equal to C, it will never touch C. That's why we've used the inequality less than and not less than or equal. Because we want to get as closer and closer as possible to that value and on the function. So remember when I said the arrow, right? X approaches C. So x is approaching C in both directions. Okay, let me use another color. So x approaches C from the right of C, and x is approaching C from the left of C. So that approach is why we use an arrow. Okay, so x is getting closer and closer to C. But what's going to happen if we get closer and closer to C? Epsilon is getting closer and closer to L as well. So f of x is getting closer and closer to L. Okay? And how does that look like in the function? Well, is this. We're going to get closer and closer to that value. Okay? So that's what our limit is. Every time that I get closer and closer to my value in x, I'm getting closer and closer to the value of in L, in f of x. Okay? And that's the definition of limits. Okay? Now, when would a limit not exist? When the function is discontinuously separable, or by jump discontinuity in that value. Okay, I'm gonna make a video for that. So if you want to watch that video, go ahead and click next. I hope you enjoy it. I know it's been a long video, but like I said, I want this to be as clear as possible. If you liked it, subscribe and motivate and share with your friends. you can go to my website and see my my tutoring services. So thanks again. Have a good day.